we've been finding tangent planes to surfaces, but one thing we might want to know about them is their angle of inclination. We want to know that because we want to kind of see how far off it is from the surface. And if you do that, you can think of this theta over maybe a path. If you can see how that theta is changing, you can actually kind of get an angular rate. So one of the reasons you might want, so one of the things you can do is if you get that tangent plane, it helps you kind of see how things are changing. But to find that angle, let's take a look at this piece here. If I've got some blue tangent plane and I want to see how it's angled, if I rotated it up direct, off of the flat plane here, notice that I've got this k vector, it's parallel to the z-axis, and I've got the normal vector coming out of it, and there's some angle between that normal vector coming out of the plane and the k vector that is that's always pointed straight upward. So to get that angle between two vectors, we have to go all the way back to some of the things we originally studied. That if we take the dot product of two vectors, it's equal to the magnitude of each vector times the cosine of the angle between them, or you could rewrite that as the cosine of the angle between them is equal to their dot product divided by their magnitudes multiplied together. So if we take this here and we say, okay, using this same argument here, we have this dot product. Now, that's not really I double lined that, but that's really a single line. So if I take this over, so that's like u dot v, n dot k, divided by the magnitude of n. Now you might say, well, why not the magnitude of k? And the answer is because the magnitude of k is 1, right? It's 0, 0, 1, so the magnitude is equal to 1. And you might ask, well, why do I have an absolute value? And the reason ends up being that if you had something like this, or you had something like that, it would have the same offsetting angle relative to the k vector. It also has to do with the fact that if you rotate this like another 180 degrees, you end up with the same offsetting vector. So for practical purposes, just know that that is a positive quantity, or a non-negative at least. But if we need that normal vector, remember the gradient can give us that normal vector. We can compute the gradient at that point on the surface, and that gradient will give us the normal. So if we do that, we end up with this. Now, the magnitude of the normal being the magnitude of the gradient makes complete sense. But notice in this particular case, I only keep the partial with respect to z. So why do I do that? Well, the reason is, shorthand, the gradient of f is, right, each component is a partial. So if I dot that with the k vector, then these are going to cancel because you're multiplied by 0, and you're only left with the partial with respect to z. So we take the magnitude, or the absolute value of the partial with respect to z, divide it by the magnitude of the gradient vector, take the inverse cosine, and that will give us the angle of inclination. So let's do an example of this. Let's come over here. We want to find the angle of inclination. So if we look over here, looks like we've got to compute the gradient no matter what. So this piece is kind of an afterthought. So we'll just go ahead and compute a gradient. Well, this thing, I can sort of rewrite that as minus 15 equals 0. And then my gradient is that. And my gradient specifically at the point 225 is that. So my absolute value of my partial with respect to z is positive 1. And my magnitude is 12 squared plus 8 squared plus negative 1 squared, which is the square root of 209, which I couldn't reduce when I was first going through this. So maybe you can. So then what I end up with is that theta is the arc cosine of 1 over the square root of 209, which I believe was roughly 86.03 degrees, or you can leave it like that depending on what you're looking to do. But ultimately finding that is just a matter of computing a partial and computing a magnitude of a gradient.